Today we're going to start section 2.2, and we're going to look at describing sets. In order to make sense of that, we first need to talk about what a set is. A set is simply any collection of objects. So you use the word set a lot, right? You might say something like, it's your set of friends, right? So it can be people. You can talk about objects. It's your set of classroom books, right? Like for your classes this semester or something like that. So any set of objects. An element is an individual object in the set. So if you're talking about your set of friends, it would be the individual friend. If you're talking about your set of books, it would be an individual book for a class. There's a couple of different ways to describe sets. One of them is called a listing or roster method. And with this method, you actually list out all of the objects. So I'm giving an example of one. If you wanted all the numbers that are 7 and bigger, like whole numbers, 7 and bigger, you could list them and you put the ... at the end, and that's called the listing or the roster method. Another way of doing this is the set builder notation method. So a set builder notation method, it looks like this. I'm just going to write what they are first. You've got an X, and then you put this vertical bar, and then it's going to say X is greater than or equal to 7. I'm doing the same set. And X is a natural number. So I know a lot of those are symbols that we haven't talked about or haven't talked about recently. So let me remind you what they are. This vertical bar, we read this word as such that. So these are all the X's such that. I think this probably is okay, right? X is greater than or equal to 7. The thing we want to make sure that we are being explicit about is that I don't mean like 7.1 if I'm talking about these specific numbers, right? 7.1 is not in the list, so I have to designate that. The way that I do is I tell you what the X values have to be. So the X values have to be natural numbers. So this N is standing for natural numbers. If you had a W, it would be standing for whole numbers, which you could use here as well, by the way. Whole numbers would be fine. This E that's sort of curly, like it's curved, means is an element of. So we will talk more about that is an element of symbol on our next slide, but that's how we read it. So we have all the X such that X is greater than or equal to 7, and X is an element of the natural numbers. So a bit of notation, the first one we'll do is that element symbol. So this symbol means is an element of. And if you put a line through it, what do you suppose it means? Yeah. I did it before, I did put equal signs. Okay, so is not an element of. The one that I gave on the previous slide was an N. So the N are your natural numbers. Natural numbers are also sometimes called your counting numbers. And if you want to think about them in either of those ways, you're wanting to think about what naturally happens when children grow, right? Or the numbers they first start to count with. So these are numbers that looked a lot like 1, 2, 3, and so on. Right? If you were to ask any first grader to count for you, they're always going to start at 1, and they will probably go as high as they can until you tell them either to stop or they start making enough mistakes that you decide that it's time to stop, right? If you include the number 0 in this set, you have what are called the whole numbers. So it includes the same things we already had, plus 0. So over here, we could have written whole numbers. X is a whole number because 7, 8, 9, 10, those are all whole numbers as well, so that would be okay. Expanding our universe just a little bit more. The letter is Z, but these are called the integers. The Z has to do with the word integers in Latin. That's where the Z is coming from. And if you remember, integers are the positive and the negative whole numbers. So I'm going to put the dot, dot, dot first. We'll start with -3, -2, -1, 0, 1, 2, 3, and so on. So on the previous slide as well, we could have said x is an integer, and it would be true. That would be another way of rewriting that, and it would be equally true. I don't know, expanding our universe just a little bit more, we have the letter Q. These are our rational numbers. Let me make one comment about how I'm writing all of them. You'll notice I'm writing the letter with a double line somewhere, like on the left or in the middle, on the Z, on the left on the Q, and the W and the N. So a lot of times when a textbook will do it, they don't do a double line. They make it like really bold. That's hard to do when you're writing, so the normal convention that you see when people handwrite these symbols is to do double lines to indicate that they're talking about the number system and not just any old set n, which they could be talking about any old set n. So you see the double lines. Rational numbers are numbers that come in ratios, okay, hence the word ratio in rational, right? So these are numbers that can be written like fractions. So for those of you who had proportional and statistical reasoning, that's where that class starts. We start with fractions, and then we do decimals, we talk about percents. We're working in the rational number system there. Within number theory, we're going to be working with natural numbers, whole numbers, and integers only. Occasionally, the rationals might kind of pop up, but that's not the point of what we're working on in this particular part of the book. The reason you use a Q for rational numbers is because a fraction is written like A over B. It's division. And the Q stands for quotient. So that's where the Q comes from for that. You might look at that still and say, okay, but why aren't you using R? And the reason you're not is because R actually has another meaning. We use the letter R for real numbers. And real numbers include all rational, so the ones that can be written like fractions, and irrational. Irrational numbers do come up. They come up in geometry. They come up maybe a little bit in proportional and statistical. But irrational numbers are things like square roots that are not easily simplifiable, right? Like square root of 4 is easy, that's 2. But square root of, say, 5, not so easy. It's not able to be written as a fraction, so it's called an irrational number. You also see the number pi pop up, at least in geometry you do, right? When you're talking about circles and things like that, you see the number pi. Pi is also an irrational number, so it's a little bit more of a bigger expanse of our universe. But like I said, we're going to be sticking with the numbers up here. These are the types of numbers we work with in number theory. All right, so using these two types of methods, the listing or roster method, and then the set builder notation, we're actually going to talk about these particular ones. So the description that they give us is the set of natural numbers less than 5. So there's two pieces of information here that are important. One is that we're talking about natural numbers as opposed to, say, real numbers or integers or whatever. And the other one is that it's less than 5. So the listing or the roster method is the one that we just list all the numbers out. So what is the smallest number that's a natural number and it's less than 5? It's 1. And I'm going to list them until I get to 4. Whoops, I skipped 3. That's not good. Let's get that one in there. This is the listing or the roster method for this description. All those numbers are natural numbers. They're less than 5, and I have included everything. Right? 0 is not included because 0 is not a natural number. It's a whole number, but it's not a natural number. Don't get the negatives. Those are integers, not natural numbers. And then if I were working with set builder notation, it always starts out with the curly brace. I'm not curly bracing very well today. That's better. an X, and a bar. So it always starts out like that. There's nothing special about X, by the way. If you want to use a different letter, you're welcome to do so. And then we need to have two pieces of information. The two pieces of information are the pieces of information that are actually underlined, that I underlined in my descripting above. And it really doesn't even matter what order we put them in. So if you want to talk about them just in the order they're listed, we can say that it's a natural number. So X is a natural number. You can list it first if you want, doesn't matter. And then we have to do the descriptor that X is less than 5. N means natural.
Or the E.
This means is an element of. It tells you that it's included in those natural numbers.
So that's essentially our is.
Yes, it is an element of. So X is an element of, or it is included in the natural numbers. Yes.
So instead of like writing like on the roster method the 1, 2, 3, 4, then if you did the X is an element of natural numbers and X is less than 5, X could be replaced by either of those numbers?
Any of those numbers, and it would be a true statement. You're right. Yes. Any other questions on that one? Okay. A couple other definitional things are popping up at this point. If you look at the top one on this slide and the bottom on this slide, they use words that in English we use to mean the same thing, but for the purposes of number theory, they don't. The first one is equal sets. Equal sets are two sets that contain exactly the same elements. Exactly the same. They're identical. So if we were to think about this and we were to describe two sets, you could talk about myself, Dr. Hand's kids as a set. And I'm going to use my husband's name, Pastor Jeff's kids. And these would be exactly the same group of people, okay? Exactly the same group of people. We have the same children. So these are the same group of people. A one-to-one correspondence is what happens when you pair groups of things together, okay? So you have two groups of things, you're pairing them together in a one-to-one fashion. So imagine like if you got a whole bunch of guys and a whole bunch of ladies out and you went on dates and you paired people up, right? That's what a one-to-one correspondence is. It's a pairing of things where exactly one element pairs with another element. Okay, so there's no groups of three, nothing like that. One pairing together. So when that happens, and you're able to do that with a group, two different groups, two different sets, you have what are called equivalent sets on the bottom. And I'm going to fill something in the middle here, but let me just show how this is related. So equivalent sets are two sets for which there exists a one-to-one correspondence between them. In other words, they have the same number of elements. Okay, they don't have to have the same elements, just the same number. So if you were doing a one-to-one correspondence, and we'll do, we'll just do the numbers 1, 2, 3, and they're in a set. And over here I have in this set the numbers 6, 8, and 12. Okay, numbers, letters, people, books, I don't care, it doesn't matter what you choose the two sets to be. If they have the same number, there's some kind of way that you can pair things up. Doesn't matter what the pairing is, but a pairing exists that matches one item of one set to exactly one item of the other set. Now, it's worth asking, well, how many different pairings are possible, right? And the answer depends on how many different elements you have. So when we look at this one right here, how many different one-to-one correspondences are there between two sets with 6 elements? So let me actually draw a picture of 6 elements, and I'll just do the numbers 1 through 6. And I'm going to do letters in the other one. I'll do A, B, C, D, E, F. And we're going to consider the numbers one at a time. If I start with the number 1 and I pair the number 1, how many different options can number 1 be paired with? 6. Okay, there's 6 different options. I could put them with any one of those 6 and I would have 6 different options for person 1. I'm going to write that 6 down. Once I've paired it up with somebody, and it doesn't matter who, I'll just pair it straight across, we go on and we consider the second element. How many different options does the number 2 have to be paired with? Only 5, right? Because I already paired up, in this case the letter A is no longer available for pairing because it was already paired up with the number 1. So now there are 5 options for number 2. And again, it doesn't matter which one I pair it with, but let's just pair it with C. Now I'm down to to 3. How many options does the number 3 have? 4, right? 4 different letters now have no partner yet. And without continuing to show that piece by piece, can you guess what happens after 4? 3, 2, and 1. The same thing would happen if you brought in 6 guys and 6 girls, right? First pair leaves, guy, girl leaves, there's only 5 choices left for the next girl to choose. Second pair leaves, there's only 4 choices left for the next young lady to choose, and so forth. So what do we do in order to find out what this 6, 5, 4, 3, 2, 1 is actually used for? Well, we're actually going to be multiplying them together. So we're going to multiply this result, or multiply to get this result. 6 times 5 times 4 times 3 times 2 times 1. And what is that? Does anybody have our calculator today? You're right, it is 720. So there's 720 correspondences. So is it any wonder that it's difficult to find that right person for you, right? There's all this pairing going on. Some people are available and some people are not. At any given point, that might change. It's a lot of correspondences, and that's just 6 people. How many people are on campus? A lot more than 6, right? A lot more than 6. Does anybody recognize that 6, 5, 4, 3, 2, 1 from any other math class you've seen before when they have that sort of a patterning going on? Prop and Stat does it. Do you remember what we call it?
Oh, it's didn't ask.
We did it with permutations and combinations. You're right. What's it called?
If you didn't ask, I could have told you.
It's tip of my head.
It's a factorial.
Yeah.
Yes.
It's called a factorial. This is just a freebie. This is not because it's included in this section, but just as a reminder or a connection for those who have seen it before. If you see an exclamation point, that's the notation for factorial. It means that you take the 6 and multiply it by every natural number below it until you get to 1. So if I see 6 factorial, it means 6 times 5 times 4 times 3 times 2 times 1. If you have a graphing calculator, and most scientific calculators actually have that symbol for factorial in them as well, just a fun fact. So this is 6 factorial. That's where it's coming from. All right, a little bit more vocabulary. A cardinal number is the number of elements in a set S. And it is written with the letter N and then the set in parentheses. Number of items in the set S. A finite set is a set where the cardinal number is a whole number. It could be large, right? So if you were talking about the set of students at OBU, I don't even know what the number is this year, but it's like 1,400 something or thereabouts. I mean, a traditional undergraduate kind of students kind of thing. So you say 1,400. So it can be a finite number that's large. You could talk about, at least at any given moment, what the deficit is for the federal, budget or something like that. It could be a really large number. It's still finite. An infinite set is a set for which the cardinal number is not a whole number. So if you were to talk about how many whole numbers are there? Well, there's infinitely many, right? I put the dot on the end for that very purpose to indicate that it continues on forever. That's an infinite set. And then the empty or the null set is a set that has no elements. Okay, no elements would mean it has a cardinality of 0. And the empty set is written one of 2 ways. You can draw curly braces with nothing inside. It's a very natural way of thinking about it. Another notation that we see used is a 0 with a slash through it. And this actually is the reason why I get a little bit picky about people using the 0 with a slash through it for their number 0, is because the 0 with a slash through it has two different kind of interpretations depending on what math you're working with. If you're working with this math with set notation, it has this idea of this empty or this null set. It doesn't mean 0, it means an empty set. In algebra, it actually means no solution, not 0. So it has a couple of different notational meanings that are not 0. It is worth noting, and you can write it and then mark it out, that you can't do both things at the same time. This is a big no-no. Okay, we don't put the empty set inside the curly brace set. Okay, it's one or the other. So what we're going to do on the next 4 examples is we're actually going to find the cardinal number. I'm pretty sure I adjusted this on my slides, but I don't know if I adjusted it on the notes. Can somebody tell me, do you have an A equals, a B equals at the beginning of yours?
Mm-hmm.
Oh, good. I got it adjusted in both places. But every time I would come to it, I would actually put it in when I talked about it, then I never fixed it after class. So we have 4 different sets we're going to do, and what we're doing is we're finding cardinality. So cardinality is actually a simplified thing that we've already done. Like we've already done it in a different place where we did more than that. We did it when we talked about Gauss. So remember when we did Gauss's method back in section 1.1, and we talked about how do we figure out how many of these numbers we have? That's the same thing as what we're doing here. So we look at the arrangement of the numbers. In this case, it starts at 9, it goes to 99, and it's including everything along the way, right? So if we're trying to figure out how many we have, what we do is we take, so this is the number of items in set A. That's the notation. We take the ending number 99, and we subtract off the number in front of the one we have in the pattern, whatever the pattern is. So this pattern is every single number, which means what's number in front of 9? 8. So 99 minus 8 would be 91. So the cardinality of set A is 91. Okay. Set B, it actually skip counts. Skip counts by 2s, or you can say it's all the even numbers. Any of that's fine. So when we're finding the number of items in set B, we have to be careful on 2 counts, like 2 different things we have to be careful of. One thing we have to be careful of is that we recognize that when we do the subtraction, we look for the number that's previous in the pattern. The second thing is that we have to notice what we're skipping by. So here we're skipping every other number, right? We're jumping by 2s, so we have to divide by 2 when we look at that as well, because we only had half the numbers between 2 and 2002. So we take our 2002, always the ending number. We subtract off what in this case? 0. It's not a very exciting subtraction, but it is 0. And then because I'm skip counting by 2s, I would divide by 2. So what is 2002 divided by 2? 1001. Yes?
So did you get 0 because the next number that would be in front of 2 is 0?
Yes.
Okay.
Like that. Mm-hmm.
Okay.
Yep. Okay, C is interesting because it looks like somehow it's harder to work with because it's got that set builder notation, right? But if you really think about what it's telling you to do, the set is not 1, 3, 5, 7, 9, and so forth. The set is actually like 1 squared, 3 squared, 5 squared, all the way up to 99 squared. But do the squaring of the numbers change how many numbers there are? No, it's completely irrelevant. It changes the elements, but it doesn't change how many elements I have. So I can very much do the same thing with the numbers from 1 to 99 as I did when I went from 2 to 2002 or 9 to 99. I just am counting how many of them there are. So as I'm looking at this, my number of items in set C is the 99 at the end minus what number comes in front of 1 in this sequence? It's actually -1, so that's a little bit awkward, but it is -1. So we have minus a -1. And once again, we're skip counting by 2s. It feels a little more awkward because they're odds instead of evens, but we're still skip counting by 2s. So what is 99 minus -1? 100, because it's really plus, right? And 100 divided by 2 is 50. There are 50 numbers in that set. They aren't 1, 3, 5, 7, 9. They're 1 squared, 3 squared, 5 squared, so forth. But the number of them is still 50. The last one actually is quite different than the first 3. I'm not counting things in quite the same perspective or fashion. This one says, I want all the x's where x satisfies this equation. X has to equal x plus 1. X are natural numbers, but x has to equal x plus 1. No, it is not possible. Right? If you take a number and you add something to it, it changes it every single time. Right? If you add the number 1 to it, it changes it every single time, no matter what you started with. So this is actually the equivalent of the empty set. It's a set with nothing in it. There is no solution, in other words. Now, that doesn't mean that the number of items doesn't have an answer. Its answer is simply 0. The number of items in set D is 0. Yep, Jordan?
So if we got a question like this on homework, would you want us to put 0 or empty?
Depends on the question and what it's asking. This question asks you to find cardinality. The cardinality means how many items are in the set, so the answer is 0. If it asks you to somehow simplify the set or to write the set out, that would be the empty set. All right, we're going to do just a little bit more vocab, and then we'll call it quits for today with the last example that fits into that vocab set, and then we'll pause. The rest of this section is going to talk about Venn diagrams. Venn diagrams are diagrams that are used to illustrate ideas in logic. In particular, they typically have circles and rectangles. And so you see things like a rectangle with sorry. That's what I want. With a circle inside of it. Doesn't have to be so fat as that, but the thickness of my line is funny. But sometimes there's more than one circle. Sometimes the circles overlap, sometimes they don't. But Venn diagrams are a way of organizing information where we have circles and rectangles. Those are what we use visually. The universal set is the set that contains all the elements that are under consideration. So in terms of Venn diagrams, the universal set is the big rectangle. And the complement, if this, I'm going to draw it better now that I have a reason to have it in there. Okay, if this is my, I'll move it into the circle. If this is my set F, so all the items in the little circle are items that are in set F. Then the last one talks about, given this set F, the complement is all the elements in the universal set that are not in set F. So they have to be inside the rectangle but not inside the circle. So you have something that starts to look like a donut hole, right? So you have this hole in here. So this right here is the complement, and I'll label it as such as well. This is, I said that I would. Pull down another tab. F complement. And, sorry, can't remember. Oh, I haven't written it yet. Let me see how this book does it. A bar on top. Yes?
Wait, okay, so the U in the rectangle?
The U is the entire rectangle.
Okay.
The F bar is just the red part.
Okay, and then the F inside the circle?
The F inside the circle is a set F.
Okay.
Okay? So we're talking about something where we, like for example, do I have the example next? Yeah, let me actually do the next example, and I think it'll answer the question more descriptively because of what it is. So let's take, for example, U is the set of all the students at OBU. And A is the set of all who are graduating. We can say graduating this year to be specific if you'd like. Okay? So you've got all the students at OBU. Not everybody's graduating this year, right? No, not everybody's graduating this year. But the set that is the complement, and I didn't write it over here, but the complement notation is written with a bar on the top there, F complement. Other books have a couple other notations just so that you're aware if you ever happen to see it. Sometimes they put this little accent mark or an apostrophe kind of symbol, or sometimes they'll put what looks like a superscript with a C, or power that's a C for complement. Our book uses the bar on top. So we'll use the bar when we're doing it. This one is actually telling you that A is the set of all those who are graduating, and they want us to find the complement, namely A bar. So if A is the set of people who are graduating, of the people who are at OBU, what would A complement be? Yeah, it's the students at OBU. See, it still has to be students in OBU. Who are not graduating. Okay, so the whole idea of it being still inside my rectangle is the fact that I'm still talking about OBU students. Because my universal set, the people I started to talk about to begin with, were university students here, right? Like that's who we're talking about. And then I exclude the people that were described in set F, which is all those who were graduating, which means I'm left with all those in this case who are not graduating. Okay? So we do this all the time. Like in my house, I can talk about all of my children, like my family, and I can talk about everyone who's able to drive, right? Talking about everybody who lives in my house. There's 7 of us right now living in the house. 7 people in the house, right? But there's only 4 that can drive. So my other 3 cannot drive. They would be the complement of that. You can talk about separating by like gender. So you have the set of all the people in my house. I'm using that as an example because there's not a lot of like diversity in this particular room in terms of gender, just saying. So you talk about all the people in my house, right? And then you can talk about A being the set that's male. And then you can talk about the complement, which would be all the females. But it's still the people that are among the 7 that are in my house. So that's what Venn diagrams with this particular notation to start with are talking about. So we'll continue our discussion of Venn diagrams next time, but subset's a pretty good place for us to pause. And so we're going to pause there and we'll pick up on Wednesday.